All right, welcome to CSE 215, Discrete Structures. This is Lecture 1. So we're going to talk about set theory today. Some of this may be review for some of you or most of you, but we'll eventually be getting into aspects of set theory that are probably going to be new. So stick with it through the familiar parts and we'll get to the more novel stuff pretty soon. So basic definition, what is a set? A set is basically a collection of things. Okay, this is a very loose definition. So it could be, for example, a set consisting of the letters A, B, and the number 2. And we write a set with these curly brackets, and we generally list the elements inside. I could make another set. I could make a set consisting of a pencil and a USB cable. That's a set containing 2 things. Perfectly fine set. But usually we'll deal with sets that involve mathematical-like things. But we'll have to be careful eventually because this idea of a set is simply a collection of things can get us into trouble, and we'll play around with that later. An important thing to note about a set is that it's unordered. So this set is exactly the same thing as this set, right? It's not the order in which these things are listed, it's just a collection of things. And for the same reason, we would not want to write something like this. Because what is this saying? This is a collection of things containing B, A, and 2. It either contains an object or it doesn't contain an object. There's no such thing as containing the object B twice. So this would be an inappropriate notation to write. And if we had a set that somehow we added B to it, but it already contained B, it would be just like this or like this. We don't list an element more than once. So a set is basically saying, is something a member of the set or not? And we can define membership with this epsilon symbol. And for example, if we call this set S, we could say that A is an element or belongs to the set S. And similarly, we could write the symbol 2 belongs to the set S. But we might write the symbol 3 does not belong to the set S. So this is the membership symbol, saying that something is a member of the set or is contained in the set. And we put a line through it to say this is not contained in the set. So some typical examples of sets we'll work with, for example, the integers are the set consisting of -3, -2, -1, 0, 1, 2, 3. And I can just list some dots on either end here to say this pattern repeats indefinitely. So this is the set of all positive, negative, and 0 integers. And we have a special symbol for that. It's this funny looking Z with this extra bar on the diagonal line. This dot notation, if it's clear what we mean, it's fine to use, but sometimes it's not always clear. For example, we might have the set 2, 3, 5, 7, ... And it's not necessarily clear what I mean by this. I might mean all the odd numbers plus 2, but in fact I'm just thinking of all the prime numbers. So be careful with this notation. Unless it's really clear what you mean, we probably want a better way of defining what we want. So we can talk about a notation where we use a formula or some sort of method for describing members. So for example, we could say that this funny symbol Z equals the set of all X such that X is an integer. And this colon, which is sometimes written as a pipe, we can take as meaning such that. So this is defining a set consisting of all possible things X such that X is an integer. So it's exactly 0, 1, 2, 3, -1, -2, -3, and so on. We could also say E equals the set of all X such that X is contained in Z, which means X has to be an integer, and X is divisible by 2. And so we've just defined the set of even integers, positive, negative, and 0, using this sort of notation. It's the set of all things X such that X is a member of this set Z, the set of integers, and X is divisible by 2. So it throws away 1 and 17 and negative 5, but it keeps 2, 4, 6, 10, and so on. So we'll use this notation such that quite a bit when we define sets. All right, some terminology. If we have a set consisting of a single element, that's called a singleton set. And we'll have reasons to talk about that in a little bit. If we have a set consisting of no elements, that's called the empty set. And sometimes it's a little awkward to write these curly brackets with nothing inside. So we also use the symbol of a 0 with a slash through it to mean the empty set. And so we could define some sets that are empty. For example, the set of all x, such that x is less than 0 and x is equal to the absolute value of x. So we're looking for negative numbers that are equal to their absolute value. Well, we know if we have a negative number and we take its absolute value, it negates it, it turns it into a positive number. So we're basically looking for negative numbers that are equal to the positive version of that. And there is no such element that makes that condition and that condition true. So this is a fancy way of defining an empty set, right, or the empty set. All right, so let me give you some other notations that we'll encounter fairly frequently. So the set n equals the set of natural numbers. And these are integers which are bigger than or equal to 0. And in some textbooks, natural numbers don't include 0. They're only positive integers. In other cases, you'll see that the natural numbers are defined to include 0. So that can be a bit ambiguous. Z is the set of integers. R is the set of real numbers. Q is the set of rational numbers. And C is the set of complex numbers. Okay, so integers, these are just whole numbers. Real numbers are like negative 2.718. Rational numbers are things that can be written as m over n, where m is an integer, and n is an integer, and n is not equal to 0. So they're fractions. Complex numbers are like 2 plus 5 times the square root of negative 1, or 2 plus 5i. Or if you're an engineer, 2 plus 5j, because we use j for the square root of minus 1, because we use I for current. So we're not going to worry too much about complexes. We'll mostly be dealing with integers in this class, but we will sometimes talk about real numbers and sometimes about rational numbers. So those are some common sets that we'll throw around with those symbols, and there'll be other ones that we'll define as we get to them. So other ways to build sets, and this one you're probably familiar with. This is something called interval notation. And so let's think about real numbers. And here's a symbol you've probably seen before, bracket A comma B. And this is defined to be the set of all things x, such that x is bigger than or equal to A, and x is less than or equal to B. So if we're working over reals, this is basically a little segment of the real number line. If this is our real line, and this is the point A, and this is the point B, this interval is basically everything in between here, including those endpoints. So this is called a closed interval. The sort of other end of that is something that we call an open interval. This would be the set of all x such that A is strictly less than x, and x is strictly less than B. So that's an open interval. And on a number line, if this is the point A and this is the point B, it excludes those endpoints but includes everything in between. And we can also have half open or half closed intervals. We could say bracket A comma B parentheses, or parentheses A comma B bracket. And the bracket basically means less than or equal to or greater than or equal to. And the parentheses means excluding the actual point A or B. So you can imagine what those mean. Now, sets can contain almost anything, including other sets. So for example, here's a set containing two elements. The first element is a set of integers, the second element is a set of reals. And you need to kind of detach from your natural tendency to try to process things, right? This is just a set containing two things. Here's the first thing, here's the second thing. It's not relevant, it's not significant that things that are integers are also real numbers, right? There's no sort of overlap here. This is just like the set consisting of a pencil and a USB cable. Well, this is a set consisting of the integers and the real numbers. This thing and that thing, two elements, okay? And it really goes no deeper than that. So avoid the temptation to sort of like start trying to overlap these things or combine them or say this is the same as R or something like that. Just a set, two things. Here's one thing, here's another thing. Alright, so next video we're going to start looking at some of the operations and analysis that we can do on sets, starting with equality.